Hello? Hi. Yes, no, it was true. I'm really, really bad at both crosswords and comet knowledge, and so that was bad. Also, I did come from MIT, but I have not yet slept, so be tolerant. Ooh, let's play. Thank you. So yes, I'm an astrophysicist. I'm actually specifically a quantum astrochemist. But today what I really want to talk to you about is what we actually see when we look at the light from stars and planets around them, and how to decipher that to try and find signs of life. Be that the sort of life you're familiar and came to love by being on modern Earth, or more unusual, strange life forms. So we are actually, as a species, very close to finding a planet that may be habitable, even inhabited. But we're not quite there yet because it's really hard, but we are still surprisingly close. We get to be the generation that is the closest. And to kind of guide you to how scientists got this far in the great exploration of alien worlds, I'll tell you how I made it here. So I actually remember exactly where I was when I decided to become an astrophysicist. I was 12, and I was watching a solar eclipse with my parents, and my parents, who were very lackadaisical and never on time, were telling me exactly at which time every phase of the eclipse would happen. And I was so confused that they were being so punctual, and then even more confused when, as they said, like magic, it just happened exactly as they predicted. I couldn't believe that we as a species, and like my mum in particular, could predict the movement of the heavens like this. That ability to know the skies without leaving the Earth felt then, and still does, like the greatest power imaginable. And I wanted it. And my parents tell me it's a real job you can get paid to do. Very little, but you can get paid to do it. So at that point, that was it. I was going to become an astrophysicist. And then this came out. Now, I don't know if you know it, it's a book by Carl Sagan, but also a film with Jodie Foster and Matthew McConaughey playing a hot priest. But in the story, Ellie, who's this girl, is encouraged by her dad to follow her passion in radio astronomy and becomes an extraordinary astrophysicist. She's looking for signs of an intelligent alien species, and she gets a message coded in prime numbers from space. Now, prime numbers can happen accidentally, and so by receiving this message, she knows this message must come from an advanced alien civilization. Now, I won't give you any spoilers, but it was at this moment that I realized knowing the skies and how they move was just the beginning. You could get paid to look for aliens. And of course, I thought I would just be doing this, doing really cool space floaty things, or at least I would be doing this. And really, I wanted to be doing this. But in the end, I settled for this, because looking for aliens is really hard, and actually sometimes really quite boring. And if you look for aliens the way Ellie did, which is waiting for these intelligent interstellar messages, then it can be quite difficult because, as Sarah pointed out, we haven't heard anything. It's been really quiet. And we know we should be hearing something because we ourselves have been sending messages into space for a long time. We've been sending radio signals for over 100 years, and we've been sending audiovisual signals since our first strong television broadcast in the 1920s. So if there are aliens out there, some, maybe not all, but some would be inadvertently or otherwise sending signals into space, and we should just be able to listen carefully. But we haven't heard anything. And that is in itself quite depressing, particularly for a girl that decided to become an astrophysicist, especially to do this. But I want to get a sense of you as an audience. How many of you actually do think there are for sure aliens out there? Show hands. All right, it's a really optimistic crowd, so I can work with that. Me too, but I actually think that that question does miss out the point that Sarah pointed out, which is interstellar distance, communicating across interstellar distances is something we have only been doing for such a short period of time. It seems quite arrogant to expect all these other alien species to be doing the same. The planet has been teeming with life for billions of years, and that life is sending out their own types of messages. And microbes, that Sarah pointed out, have their own metabolites, the gases they release. But our whole biosphere is a message. And so you can reverse this problem and understand how we could look for an alien biosphere by figuring out what they would see if they looked at us. If they looked at us and they were at the edge of the galaxy, this alien astronomer, and we would be about 2/3 out, about there-ish. And from their perspective, our sun, so special to us, isn't special at all. It's just one of 300 billion bright white lights. But that white light, seemingly so fundamental and pure, is exactly the key that unlocks the secrets of these planets orbiting around the stars. Because white light is only pure until you crack it open. With a drop of water or a prism, white light shows what really is within it. And that's the rainbow. And the rainbow isn't just all the colors, the 7 colors. It's actually all the reds and all the violets and all the infinite colors between them and beyond them. It's the red and the ultraviolet where the eye can't see. So if that alien civilization pointed their very expensive prism at our sun, this is exactly what they would see. They would split our sun's light full rainbow and see not just the color of the rainbow, but they would see that some of the light would be missing. Parts of the rainbow would have been absorbed by the atoms and even the molecules at the edge of the sun, where it's cool enough and molecules can survive. And so with very fundamental and yet universal knowledge of molecules, they would be able to tell which molecules were causing each one of these shadows, because molecules behave uniquely, no matter where in the universe they are. And this way, they would know the composition of our sun. This is our sun's spectral fingerprint, and this is unique to us. Other stars will have different compositions, different atoms and different molecules, and so different rainbows. But if that alien civilization was patient, they would notice that every 12 years, a few additional shadows would appear and then disappear. And 12 years later appear and then disappear. And these shadows will be caused by the molecules in the atmosphere of Jupiter, as light crosses through it and molecules within that atmosphere absorb a few more wavelengths of light. And they would be able to know what Jupiter is composed of. And if they were really careful, with technology just a bit better than ours, they would notice that every year, a few additional weaker shadows would appear and then disappear, and appear and then disappear, and these would be caused by the molecules in our own Earth. And you'll be able to study that change, these new shadows, absorption lines in the sun's rainbow, and find out exactly who we are and what we do. You can think of our own biosphere as an unintended planet-sized message shouting to the galaxy that we are oxygen-reliant life forms with rich life cycles, vast inhabited oceans, and also that we pollute an awful lot. And we can do the same to them. But when we do the same to them, what do we look for? Sarah pointed out that it's not as simple as looking for oxygen. You can look for oxygen, you can look for methane, you can look for carbon dioxide, molecules that we know and love from life on modern Earth. But as Sarah pointed out, isolated molecules are not enough to show life. And more importantly, they all have false positives. Now, this is not a cruel game of astrobiology. There's a reason why the molecules that life loves are also produced by things like volcanism and photochemistry and other geochemical processes. It's because they're exploiting the same chemical gradients as we are. These are molecules that are easy to make from a chemical perspective. So life makes it, but other things make it. And the way to solve this was also hinted at by Sarah. Context. You need to get chemical context on these molecules. You find oxygen, that's a promising sign of life. You find oxygen and methane, that's an even more promising sign of life. So you can resolve these false positive scenarios for the molecules of life as we know it by detecting other contextual molecules around them. But of course, that works if you can detect all of these molecules. So find oxygen, great. Find oxygen and methane, even better. Get a full chemical network of that planet, and you can map it, and you can understand what's going on there and at the surface. But this will only help you, even if you solve every possible false positive scenario for all the biosignatures of life as you know it, if you find life as you know it. What if life is just not as you know it? What if life produces totally different biosignatures to those that we're used to? Life as we know it is likely only one island in the vast archipelago of possibilities for life. In our galaxy alone, there's a huge diversity of stars. Orbiting them, a huge diversity of planets. And in our planet alone, a huge diversity of life. So it isn't a big leap to think that life itself can arise in a huge diversity of forms, and that life will produce unexpected biosignatures to those that we're used to. For example, this is phosphine, my very favorite molecule. I met phosphine when I was about 23, and at the time it was quite an unusual molecule to think as a biosignature, because it's a nasty, nasty little thing. It's famous for being just outrageously foul smelling. It's incredibly toxic, it's highly flammable, and really it's just kills everything. In fact, because it kills everything, the reason it's famous-ish on Earth is because it's widely used as a fumigant. It's toxic to most life forms, and it kills in a variety of gruesome processes, all of which have to do with the phosphine molecule bonding with the enzymes crucial for oxygen metabolism. In fact, because it's such an effective and horrific killer, it was used as a chemical warfare agent in the First World War. It's awful. The other thing it's famous for is that on Earth it's released as an unfortunate byproduct of methamphetamine production. So it just gets worse. If aliens did spot it on Earth, they would know that there's life here, because only life would have insecticides, war, and meth. So it's good as a biosignature, but it's pretty awful as a molecule. But as I was researching it, I found that for about 100 years there had been quiet but regular mentions of it being found all over the place. And that's deeply controversial, because it's so toxic to life, it is so hard to make, chemically speaking, that we should find it nowhere, and yet we do. We find it ubiquitously throughout the globe, and in some places in strangely large quantities. Places like sewage, marshlands, rice fields, lake sediments, the intestinal tract of fish, the intestinal tract of babies, the feces of penguins, the flat of badgers, and actually the intestines and excrements of many, many, many animals. And there's a reason phosphine is found in all these places. These are ecosystems that all have one thing in common, and that is they're anoxic. They're without oxygen. Most of Earth's life loves oxygen, but there's a few niche ecosystems that don't care for oxygen, and there phosphine is not so evil. It is only phosphine's relationship with oxygen and oxygen-loving life that makes it so toxic. Now, we, overwhelmingly as a planet, we chose oxygen, but maybe had we chosen phosphine, then we couldn't have oxygen. We would have been very different. We would have been more of a sewage planet, intestine planet, which sounds bad to us, but we probably sound disgusting to them. And so, you can imagine a planet like Earth during the Carboniferous period, but without oxygen, a wet, tropical paradise. And that planet could potentially produce loads of phosphine by its rich anaerobic biosphere. So, you know, okay. Okay, oh, sorry. So, phosphine, not so evil, as long as you're willing to hate oxygen, which plenty of species are. And in this case, not only would it be an amazing way of finding alien life, oxygen-hating alien life, but it has the added advantage that because it is so hard to make, it's the sort of thing that only life can do. Things that are hard to make can only be made on purpose, and life will make things on purpose, but geochemical purposes don't. You can't make phosphine accidentally. Now, I should point out that phosphine, although very exciting for all the things I just mentioned, it is still hard to detect, because no amount of biomass is likely to make a lot of it. It's hard to make. Which means it's not likely to be very abundant. Not being very abundant is not a good reason to not look for it. You can look for alien life by detecting phosphine on temperate planets, but it will be hard to find it. But whether you're looking for popular biosignatures like oxygen or methane, but still have to consider less abundant molecules to give them context and resolve their false positive scenarios, or you're considering less abundant molecules like phosphine that are less abundant but have no false positives, the fact remains we need to be willing to consider more molecules, whether they're abundant or not. It is by considering a full, holistic atmosphere that we can get to a point where we can detect life. Because life will not be detected with a smoking gun unless we find CFCs. Life will be detected with a degree of certainty. It will be a probabilistic event. And if we want to improve our odds, we need to consider the big picture. Not just one or two molecules, but every molecule that can together help us reduce the uncertainty in the detection of life. And when I say every molecule, how many molecules do I actually mean? Well, to figure out how many molecules you need, the right question to ask is not what life might be, but what life must do. On Earth, all life does one thing, and that is all life metabolizes and produces byproduct gases. So alien life can be expected to similarly produce byproduct gases. And alien life can be completely different from ours, but it still has to make use of the same chemistry, the same physics we have available to us. And as such, there's a limited number of molecules that life can assemble out of the periodic table. So our group at MIT has been trying to make exactly that list. We can take all possible molecules, and then we narrow down that list by considering only those that would be gases in the temperatures and pressures of habitable planets. Then we narrow down that list by only considering molecules that could possibly be associated with some form of life. And by narrowing down the list of all possible molecules with these parameters, we are left with a list of 16,367 molecules that life could produce and release into the atmosphere of any planet. Now, this is a large list, but importantly, it's a finite list. We can do this. And this is exactly what I've been doing. Now, to do this, you need to have to be able to detect these molecules, these 16,000 molecules, you need to have their fingerprint. You need to know how they interact with light. And to know that, you need to have these molecule spectra. So each molecule has a spectra of its own that defines how it interacts with light and which colors of the rainbow it absorbs. But creating these fingerprints, these spectra, is extremely hard. To do this, you can, for example, measure in the lab. But measuring in the lab can be expensive. It's often very dangerous and sometimes altogether impossible. You can instead simulate it on a computer, but that's also really hard. It takes millions of CPU hours on supercomputers, and it is only possible to do for some of these molecules. The reason it's so hard to do this theoretically is because you're basically studying quantum behavior. And in the quantum world, even simple problems become difficult very quickly. And because of that, out of that list of 16,367 molecules that could be produced by life and released into an atmosphere, we only understand about 600 of them. And we only completely understand a few dozen of them. The other 15,747 molecules, we know nothing about them, and we have no hope of remotely detecting them. Out of the thousands of molecules that life could emit, we have spectra, the fingerprint, for 0.04% of them. Now, you'll be relieved to know that one of the ones we do have fingerprints for is phosphine. But that's because I spent my entire PhD and most of my 20s producing a complete quantum chemical picture of this molecule. This line you see here seems simple, but it's actually composed of 16.8 billion tiny features, which correspond to 16.8 billion shadows that phosphine casts on a stellar rainbow. But now that it's done, and I'm so glad it's done, it is freely and publicly available, which means anyone can detect phosphine anywhere in the galaxy. But that's just one molecule out of those thousands of molecules. I'm just one person. And one person to do one molecule, hundreds of CPU hours, thousands of CPU hours, hundreds of GPUs, and 4 years of my life, and more sweat and tears than I care to admit. So, if I was going to target the remaining 15,747 molecules at that rate, it would take me over 60,000 years, which is too long. And I realized this when I was finishing my PhD, and at the time, I was the head of education for the Twinkle space mission, which is a very small telescope that will launch in 2022 and observe exoplanet atmospheres. I ran EduTwinkle, which mainly did outreach for primary schools and high schools. But one of the things that I was doing at the same time was I was a high school teacher, a science high school teacher in a local, severely underfunded secondary school in North London. Now, we had no resources, but any time that I got to talking to my students about my own research, we got into super interesting scientific discussions, which made me think, what if I wasn't getting spectra for all these molecules by myself? And so I created Orbits, original research by young Twinkle students, and recruited my own students to work with me and produce molecular fingerprints for those molecules from that long list of molecules that life could be producing into an alien atmosphere. And this is them. We got together and worked with 3 graduate researchers that kindly agreed to help me. And this is Team Titanium Oxide, team acetylene, and team methane, 3 molecules crucial for the understanding of alien planets. These amazing kids worked so hard and learned astrophysics, programming, scientific writing, and eventually we all published several peer-reviewed scientific articles on these molecules. These kids are now supervising new teams of new kids, and more importantly, new molecules. So it isn't just me. Now that we're all working together on this and putting a tiny dent on that list of thousands of molecules that aliens could be producing into the atmosphere, maybe we can do it in time. Because there are billions of stars out there and billions of planets orbiting them, and within them there could be trillions of species producing metabolites and releasing gases into the atmosphere, just waiting to be detected. And of course, all of this might be an awful waste of time, because maybe there is no life out there, maybe there's nothing. But to misquote Carl Sagan, the universe is a pretty big place. It is bigger than anything anyone has ever dreamed of before. So if it is just us, it does seem like an awful waste of space. Thank you.